Hello, this session is about thin film design, and I would like to show you how we can optimize low E coating for architectural glass. Before I do that, I will load a configuration that we have used already in the past when I showed you the user interface of Scout and Code. Let me just reload this configuration. And in order to save a little bit of space, I will rearrange this section that shows the reflectance and transmittance spectra, because for glass coating design we need two reflectance spectra from the front side and the back side of the glazing. So we need more. We need to show more here, and I would like to show you a new view object that you can use to display several spectra in one graph. So let's go to the tree view and take a look at the list of view elements, which I had explained in the first session about the user interface. We can delete the two objects that show the graph, that show the spectra here on the right side, and we generate a new object here in the drop-down box. The new object should be of type multiple spectra view, which is here. Sorry that it took so long. We generate an object like this, and we call it R front, T, R back, and this should indicate what we want to show with this object. Once we have generated this, we can edit this object, and you see a graph here already. I would like to set the range from 300 to 2500 nanometers with 500 points. This range will be used to display all the to generate all the data of the spectra that are displayed here, and the graphic settings are independent of this range that we just set. But I will make them showing the same region from 300 to 2500 nanometers. Tick spacing should be 250. I would like to make the height of the text a little bit smaller. The title should show the name of the spectra. Should also be written a little smaller. Sorry, that's not the title. That's actually, I can copy that. That's the y-axis. We need ticks at every 10%. I would like to use grid lines, which is frame mode number 3. The grid lines should be straight lines in white, so that the graph now here looks like this. We move it to the right, and it's still empty. We have not yet selected any objects here, but we will now do. So if we open the list of view elements, we can drag spectra to this new object and drop those spectra there. And you see now already that we have data here that are displayed, and with show list we can show the list of spectra that are shown. You can show here all spectra that code computes and also material properties like refractive index values or dielectric functions. In this case, we want to show the simulated spectra only and not measured spectra. Let's say we can compute reflectance in red and transmission in blue. That should look like this. Update. Okay. And actually what we also need is an update of the graph in the sense that it should be a little bit larger. 200 millimeters here, that's the size of the graph in this on this page here. And I would also move the legend to a different position. The top position should be 180, the left position 100. That should work here. That's okay. Maybe also the title should be drawn in using a smaller font. Good. Okay. That's almost good. We now need another spectrum. We have actually here the reflectance spectrum, which I would like to call our front in this case, the transmission, and we need to add the reflectance from the back side. So if I duplicate the front side reflectance, rename it to R back, and opening it here, I can set, instead of the angle of incidence of 8 degrees with respect to the surface normal, we go to 172. That means 8 degrees from the backside normal. If we recompute this, you see that the spectrum is really different because on the backside there is the glass and not the thin film coating. So this spectrum, this new spectrum, should also be displayed here in this multiple spectra view object. So if we go to this list, we can show the list and actually delete the measured spectrum here. Unfortunately, I renamed the reflectance spectrum from R to R front, so it's not shown anymore. I have to use the same name here so that the object finds the data again. Okay, that's how it should be. And we can now take a look at the main view and rescale this object a little bit so that we have all three spectra in one graph with legend. Okay, that's how we can work. Still, we are not going to start with design work. I would like to update the layer stack a little bit to make it more realistic so that you can directly use this configuration for serious work. I would like to add the zinc oxide layer here on top of the titanium dioxide. I explained that in the tutorial about glass coatings, that titanium dioxide gets very rough and it's not very good for the properties of the coating if we deposit the silver layer here on a rough underlayer. So it's advantageous to have a thin zinc oxide layer in between, which levels out the titanium dioxide roughness. In addition, on top of the silver model, I would like to add a nickel chromium buffer layer, a protection layer for the silver that is usually sputtered metallic as a very thin film and then oxidizes during the process of the deposition or at least some hours later on and it should ideally completely oxidize. So let's take these new materials from the database. The database of optical constants has, in the section that starts with Z, a zinc oxide model here that I would like to use. So I push it to the list of materials. I press the letter N to go to the section with names that start with N. And there is a nickel chromium blocker model here, which I would also use in this tutorial, and I drag that to the list of materials as well. So let's first update the layer stack. On top of the titanium dioxide layer, I add a thin film, let's say 5 nanometers, and we fill in the zinc oxide. And on top of the silver, I add another thin film, let's say 2 nanometers. That's the nickel chromium blocker. Okay, and now some more fit parameters. And then I will explain a little bit about these new materials. Let's delete all the parameters that we have right now and start new in this list of fit parameters selection. Let's first pick some material properties. The silver layer has one parameter that would, let's say the optical constants of silver, has one parameter which we have to update, and that's the damping constant of the electrons. I have also explained that in the tutorial about glass coatings. Basically, the damping measures how good the electrons can move, how high the mobility is, and that depends on the volume of the quality of the volume of the silver layer, but also on the surface roughness at the top side and the bottom side. So that damping constant here is an important parameter related to the quality of the silver layer. And the nickel chromium blocker, that's a so-called master model, which I will explain in a separate tutorial in detail. A master model basically has only one parameter left that controls the optical constants completely. In this case, it's the oxidation state, which I called OX, and I select that as a fit parameter as well. I will explain in a moment the range of this parameter and what it means. And in addition, I select all the layer thicknesses as fit parameters that we can modify. Good. Let's now take some limits and some starting values. The damping constant of silver typically is between 200, that's a very, very good silver, very high mobility, to 1000. That's considered to be bad. And let's start with 500, which is somewhere in the middle. Not really good, but also not really bad. The nickel chromium oxidation state varies from 0 to 1. And if we start at 0 here, then the nickel chromium is metallic, no oxygen at all. If we are at 1, then it's oxidized as much as it can be. So for our final coatings, we assume that the production has managed to have a fully oxidized nickel chromium stack in the end, a layer in the end. So we can set this parameter to 1. And okay, let's start with 50 nanometers for the tin oxide layer, 2 nanometers for the blocker layer, 10 nanometers silver, 5 zinc oxide, and 20 for titanium dioxide. The glass thickness should be 4 millimeters, and in order to optimize the coating for let's say in the design phase later on, I would like to change only a few of these parameters, not all of them, but I would like to keep all parameters here as parameters that we can change with the mouse. Only in the automatic fit, only part of these parameters should be changed automatically. So we can use this. We can set this wish in this variation column, which is usually downhill simplex. That means in the optimization, this parameter will float around and change its value to optimize the model. But we can press F5 to set the parameter to frozen, and I would like to do that for the damping constant of silver. And I also press F5 here for the nickel chromium oxidation state. And I would also freeze the thickness of the nickel chromium blocker. That is not really related to that's not a thickness that we can freely vary, because its function is to protect the silver. So we need, let's say, the 2 nanometers, but not more. So that function requires a certain thickness which should not be changed, or which is not available as a free parameter for the design. Also for the zinc oxide, that should be 5 nanometers and stay like that, so it's frozen too. And also the glass thickness should not be part of the flexible design. So we only have, in this case, 3 parameters: the top oxide, the silver, and the bottom oxide thickness that will be varied once we do an automatic fitting. So let's press F7 and summarize. We have a more realistic layer stack here now on 4 millimeter float glass. We have all the relevant model parameters here as fit parameters. Most of them are frozen. They will not be optimized in automatic fitting. Only those which have the D here for downhill simplex are changing their value in the automatic routines. On the right side, we see the front side reflectivity, where we see basically the low E stack. From the back side, we see first the glass and then the low E stack and the transmission. I'm not sure if that's clear to everybody, but the transmission does not depend on the side from where the light comes in. So in the case of transmission, we do not have to distinguish between front side and back side transmission. It's always identically the same. So we only have to compute that once. But of course, the reflectance, that is different, as you can clearly see here. So I would like to save this configuration. I have to switch on the menu to do that, and use a new file name. Actually, I would like to make a new section called Design, and this is a low E prototype. Let's say we can call this single silver low E prototype, and later on I will reuse this configuration for some other purposes. But now, for today, we are all set to start with design work. And actually, design work means that we want to optimize the coating with respect to wanted technical values, technical data. And for example, we want a high visible transmittance. So we have a coating on glass. So it's made for a window, and we want to look outside as good as we can. So we will have a wish for the transmittance and the visible spectral range. We may also have wishes for the reflectance colors. That means the colors that the coating will have when we look at it from the outside. And we will have wishes for the thermal insulation, as I have explained in the tutorial about glass coatings. That was the U value. And there will be some other values like the G value, which I will explain later on. Okay, let's first take a look at the list which is responsible for all the technical data. In the tree view, that's the list called integral quantities here, almost at the end. In the list of integral quantities, we can define quantities that we want to compute, and we can choose from a long list of possible values. It starts with a section related to color, and then there are many other properties that we can compute. As you can see here, it's a large variety of things that we can compute and optimize with code. I will discuss only a few of them in this tutorial. Let's start with probably the most important quantity of glass coatings. That's the light transmittance. This is the average transmittance of the glazing for visible light. There are two choices here concerning light transmittance, labeled T65 A and C. These are different light sources or different illumination spectra. D65 is basically something which is close to sunlight, to natural sunlight, and this is what in most cases is used to measure how much light goes through the window in the visible. So if we generate a value of this type, we have to give it a nickname, or we don't have to, but we should. I call this simply light transmittance. It will be good if our names are not too long. Light transmittance, once you type in a new name, this is used as a so-called nickname, a short name for this quantity. If you want to go back to the original name, you have to delete the text completely, and then code will go back to the original value, just in case you forgot what this quantity really was. So, but we use as a nickname now simply light transmittance. And the next column here, you have to assign a spectrum for which you want to do the computation. You can change the assignment with the F4 key or the F5 key. You cycle through all the possible settings, and we stop here at the transmission spectrum. In this column, you can select if you want to do the computation for the simulated or for the experimental spectrum. You can shift between those settings with F4. And concerning the last columns, I will ask you to wait a few minutes, then I will show you how we can work with those quantities. Okay, let's just compute this number by pressing update here. So it's 0.848. That means almost 85% transmittance that we have here in this case. And that's all we can do here. We just get one integrated value. Okay, another interesting quantity or related quantity is the light reflectance, also for D65. This is actually exactly the same quantity computed in exactly the same way, just the name is light reflectance. If we assign the front side reflectance, then we will get now here almost 8.1% reflectance. So these are the most important quantities for the glass coating. The next type of object I would like to discuss is related to color. It's called color coordinate, and that's a very flexible object. If you just generate it, it will compute L star. That's a color coordinate value for illumination type D65 and an observation angle of 2 degrees. And this observation angle is not the angle of incidence, but maybe I should explain that when we go through the possible settings here. If I click on Edit, we can give this a nickname also. This I would like to call this L star R front, or let's say L star front. Okay, and in this color dialog, we have to fix three different quantities. First of all, the type of the color coordinate. That's also a long list of possible values. Very prominent are L star, A star, B star. For glass coating design, these are certainly the most important color coordinates. They are X, Y, Z values with capital letters and small letters, LAB without the stars, something like values like chroma and U prime, Y prime, and V prime, and the RGB values that are used to display colors on screens. These are the possible choices here. Let's start with L star. Illuminants are the same that we have seen already for the light transmittance, D65, A or C. Let's stick to D65. And then here we have the observation angle. And there are only two choices, 2 degrees and 10 degrees. And as I tried to explain before I stopped it actually, these two choices mean with 2 degrees we are looking at a very small spot, and of 2 degrees opening cone angle, and with 10 degrees the spot is larger, and our eye sensitivity seems to be a little bit dependent on the size of the area that we are looking at. So the color impressions are a little bit different, and that is reflected in this choice. Let's stick to 2 degrees, press OK, and then we get here an L star value of the front side reflectance. Actually, I would like to duplicate this 2 times in order to change only the name from L star to A star front, and then we compute A star instead of L star. And for the next one, we replace the L by the letter B, and we compute B star, so that we have now a complete triple L star, A star, B star for the front side reflectance. I would like to move the transmittance a little bit upwards, and then make a duplication of these quantities. L star front should also be computed for the transmission, and then we should rename this L star T, or actually I should call this L star R front. Sorry. Also here, and I duplicate this and rename this A star T, assign the transmission spectrum here, and duplicate also the B star value so that we can compute B star of the transmission spectrum. Okay, let's sort this a little bit. Let's bring the color of the transmission spectra together. and also the color of the front side reflectance. Let's update all the numbers. Okay, that looks nice. And to be complete, let's duplicate again the L star value for the front side reflection and compute it for the back side reflectance. Move that downwards and then do it for the A star backside and assign the backside spectrum also. Move that down and finally do that. Duplicate the B star. Sorry, rename it. R back. Sorry, that was actually not really necessary to go through this dialog. Good. That's a little bit of clicking work, but I have done it now rather quick. So we have a triple L star, A star, B star for the front side reflectance, for the transmission, and for the backside reflectance. If we update the colors, they are different for the front side and the backside. Okay, that's nice. And let's now add some more quantities which are important for the following work. Let's compute what is called solar transmittance. This means an average value of the transmittance for solar radiation. This is averaged from 300 to 2,500 nanometers, and it measures basically on the average how much sunlight goes through the glazing. There are different international standards for solar transmittance, actually several of them, so that makes this list so long here. I would like to choose the ISO 9050 version for solar transmittance, generate an object of this type, and then once we are there, we can also compute solar reflectance. And in the case of solar reflectance, let's bring that down, and the transmission also. Solar reflectance is to be measured for the front side. Let's call this solar R, and the other one solar T. And here we have to assign the transmission spectrum. Let's update so we get some numbers, and you can clearly see that the solar reflectance is much higher, 21%, instead of the light reflectance in the visible. And if we press F7, here it's clear why that is. The visible light reflectance is averaged here, basically from 380 to 780, where we have a low reflectance. The solar reflectance is averaged from 300 to 2,500 nanometers with a weight of solar radiation, which is strong here in the visible, but nevertheless there are contributions from this high reflectivity, which make the solar reflectance high. Okay, these are a lot of values already, and it would be now useful to see all these values in the main view, and we can achieve that in a very simple way. We just go to the list of view elements, and we drag the integral quantity list to this list, and then there is a new object generated that has the type list view, and we should give this the name technical performance. And if we press F7, we have a list here of all the quantities that we had defined. Actually, we can press the Control key and edit this view element and change the style to this text with background color, extra color every second line. If we do that, it looks like this, which makes it a little bit easier to read. Okay, let's save this configuration using a new name, single silver low E design, although we have not yet designed anything. Just to take a look at our possibilities now. I have to set ranges here to the fit parameters, which I forgot. So let's set a range for the silicon oxide from 0 to 100, for the silver model from 0 to 20 nanometers, and for the titanium dioxide layer from 0 to 30. So let's now we can change the values. You can see that the spectra change if I tune the silver layer and the titanium thickness and so on. So I can now tune the parameters, and we can instantly see how the values change and how the spectra change. So let's now do a first little design. Let's wish that we have a light transmittance of 90%. So we can do that in the list of integral quantities. If we set a target value for the light transmittance, that's this quantity here. Let's set a target value of 0.9 and put the optimize option here, set this option to on. And now if we press start to start the automatic fitting, code will take as a fit deviation the difference between this value here and this value and square this. That will be the fit deviation, which is going to be minimized. So code will now try to make this a 0.9 as well. Let's see if that works. Press F7 and press start, and now the 3 layer thicknesses are optimized in favor of a high transmission of 90%, and we can almost get it. Not completely. Maybe we can. Here you can see the titanium dioxide thickness has reached its upper limit. Maybe we can go up to 40 and start the fit again. So now the transmission gets even higher, the average transmittance. But we need a very thick titanium dioxide, and actually this is not really reasonable, because wishing only a value for the light transmittance is certainly not sufficient. We need to have more wishes. Okay, let's make it a little bit more realistic, even more realistic. We want actually we should not optimize just a coating on glass. We should optimize a complete glazing. So that will be the next step, that we add a second glass to the model and a gas filling in between, and then we can go on with our design work. So we should really work on the properties of the final product, And suppose we have another 4 millimeter glass on the other side with an argon gas in between. So that's what I would like to define now. So we will add the two layers to the layer stack. On top of this, we generate a new thick layer that will hold the argon gas, and another new layer that will hold the silver, the top glass. So the glass should be 4 millimeters, and the argon is typically 16 millimeters. So for the glass, we can already make use of the glass model that we have. Here I would like to use argon gas, and for the optical computation, actually it doesn't really matter if we take any gas or vacuum. The refractive index is 1 concerning the real part and 0 concerning the imaginary part. That is a very good approximation for all real gases. But for the thermal properties of the glazing, that means the U value and also the G value, it makes a difference what kind of properties we have here in this gap, especially the viscosity and the thermal conductivity and so on. And so we need realistic gas values there. And we can do that in the following way. We go to the list of materials. We select as new object type a material type called gas, which is at the bottom here. So we generate a gas. We can call this already now argon 90, because we are going to define 90% argon and 10% air, which is a frequently used mixture of gas if it comes to technical applications. So if we edit this object, we get a dialog of gas properties, and here we could basically set the air volume fraction, which is 10%, and argon, which is 90%. And if we click on Update Properties, now the density, the dynamic viscosity, the thermal conductivity, and the specific heat are recomputed. And these are the numbers that we need to know to compute the U value and the G value. Okay, press OK. We can now use this argon gas and fill it in this layer stack. Okay, so this would be a low E coating, and we can now go back to the main view. The transmission is lower now because we have a second glass, so our wish of 90% is now not really very realistic, but we will review our wishes in a moment. And now, since we have a realistic glazing product, we can also compute the thermal properties. And let's start with the U value. We can go to the list of integral quantities and try to find the U value in this long list. Actually, it should be pretty much at the bottom. Here it is, just U. And if you press plus, we can probably move it downwards to the end, because it's not an optical quantity but just a thermal property. And if we press update, we have here now a value of 2.57. Maybe you remember that let's say if you have seen the tutorial about glass coatings, that the U value of low E coatings should be in the range 1.2, 1.1, 1.3 maybe, but certainly not 2.6. Actually, the purpose of the silver layer in the low E coating was to reduce the emissivity to make this U value small. And somehow this does not work here in this configuration, so something is wrong. And we can take a closer look at the U value. If we click here on Edit, we could set a nickname here again, but we don't want that, but we can just go on. And what we can see here is basically a sketch of the layer stack again, but it's a sketch related to the thermal properties. We have an outside temperature, an inside temperature, then we have an outside emissivity. This value here, 8.9, that's the emissivity of the glass surface, which is outside. Then we have basically what's called group 1. That means all the solid materials here that sum up to 4 millimeters. Basically, it's the 4 millimeter glass. And then we have the emissivity at the inside. That's also a glass surface which has 89% emissivity. Then we have the argon gas, and here that's the emissivity of the coating. And that should be very low because it's a low E coating, a low emissivity coating, but obviously it's not. It's 0.75. So here is our problem. That's not correct. The emissivity on the other side, that's again glass. Okay, so something is wrong here. And actually what is probably wrong, I can just check if I'm right with my assumption. Yes, that's the problem. The optical properties of silver, they are basically needed in the mid-infrared, where we have the emission of black body radiation for glass at room temperature. And that means we have to know the optical constants of silver for 10, 20, up to 50 microns, but the data are only computed here in this short range. So we have to use the range command here in order to go to a range from 300 to 50,000 nanometers, and maybe we should use 3,000 data points. And now we have the silver model everywhere where we need it for emissivity computations. Let's now go back to the list of integral quantities and edit the U value. Let's first press on Update. Okay, and you can see now the U value is 1.26. And if we edit this, the emissivity is now 8.6%, which is significantly lower, and that's why we get a more realistic U value now. Okay, let's continue now and take a look at this list. So now let's start to summarize our wishes that we might have. We could wish for a good thermal insulation, so we could wish for the U value, a value of 1.1. That would be nice. We put the optimize option on. So now code will take into account the U value for the optimization and the light transmittance. And let's wish here 0.85. Okay, and what code will do now, if you have, it will go through this list. Every quantity which has the optimize option on will be used to compute the fit deviation. Code will take the target value, subtract the actual value, square that difference, multiply with the weight, and then add all these numbers to the final fit deviation, which should be as close as possible to 0. So in this case, it will try to make the U value small and the light transmittance to be 85. Let's just here on the main view press the start button and see what happens. Okay, so this is now a compromise. Let's maybe we should start with a more realistic value of the titanium dioxide. I'm not sure if that will really help. Probably it will go back to large values during the optimization. Okay, the U value is 1.15. Basically, that's pretty good. The light transmittance is 79%, which is also not too bad. And let's just take a look at some other values. The color of the front side reflectance is this. Maybe we should also have a wish for the front side color. That's the color of the building that you see if you look from it outside to the inside of the building. Let's wish a slight bluish appearance, almost neutral. So let's go to the list of integral quantities. Go and A star front and B star front should get target values of, let's say, -1 each. That is almost neutral. And we bring this option to on. And, well, let's put a small weight here. Otherwise, these quantities will really dominate everything. Let's put 0.01 as a weight factor here. Okay, press F7. Press the key. Well, press the start button. Sorry, and let's see how the new color wish affects the optimization. Okay, that's not too bad, except for our wish for the light transmittance. Maybe that is too ambitious, the 85%. We reach almost 80%. The color values are almost okay, -1, that's almost our wish, and the U value is also very nice. So this is actually a rather successful fit already, which makes sense to be saved. So file, save. Okay, so that can be already a low E product that you could sell eventually. Before we go on to advanced topics in one of the next tutorials, I would like to add the G value. Okay, that was missing. Sorry, I should have done that before. Let's move this a little bit to the bottom so that we have space for another value. Let's compute and explain the G value in the list of integral quantities. The G value is related to solar transmittance. So for every standard for the solar transmittance, like standard EN 410 or ISO 9050, there will be a G value, and you can see that here. Let's stick to the ISO 9050 standard and compute G. Actually, the G value measures the following. It takes the solar transmittance, so all the solar radiation that goes through the glazing into the interior of the building, and then it adds a second number, and that second number is the heat that is transported into the building by absorbing sunlight in the glazing. Let's say in the front pane there's an absorption, in the coating and the second pane there's absorption. So the glass panes heat up, and so they start to radiate and they start to emit energy to the exterior and to the interior of the building. And these flows of energy are called QI and QE. And if you add the QI value to the solar transmittance, you get the G value. That means the total energy that is originating from the sun that enters the building. That's the G value. So it measures basically how much that number can be used to compute how much the building will heat up in the summer when we have full sunshine. So the G value is computed here. Let's move it down below the U value, and this has to be assigned to the transmittance spectrum, and then we can compute its value. It should be larger than the solar transmittance. So the solar transmittance is 51%, the G value is 61%. So here we have a strong heating effect. The coating actually heats up a lot and gives up part of its energy to the interior of the building. The G value also, if we added this, let's call this just G as a nickname, uses the emissivity as well, basically like the U value. It computes basically the heat propagation through the layer stack. And there the emissivity plays an important role because radiation exchange between the individual glass panes here is important for the total transport of energy through the glazing. Okay, so this is a more or less complete picture now for the single silver low E. Before we end this session about the introduction to thin film design, I would like to save this configuration and I would like to add some more layers to the layer stack. This was the single silver low E, and I will also cover for one of the next sessions a double silver low E stack. So we have to add some more layers. Let's go to the layer stack. It will be pretty quick because we have all the materials. I would like to use another thin film, which is another silver layer here. We can use the silver, reuse the silver model, and then we need another blocker layer, nickel chromium blocker, and we need another. We need a top layer. We can use the tin oxide at the top also. Let's use the 50 nanometers on the top. The nickel chromium should be 2 nanometers also. The silver may be 10. And the oxide in between, the center oxide between the two silver layers, that should be pretty thick. Typically that's 80 nanometers, something like that. Okay, but that was also a fit parameter. So I have to be careful because this value will not be taken because it's here as selected as a fit parameter, so it will get its value from this list. Actually, to keep the overview, I would like to delete these parameters and take a look at the layer stack once more and do a last operation before we redeclare the fit parameters. Actually, for a double silver stack, which would be something like a solar control coating or a double silver low E coating, it makes sense to put it in a different position in the glazing. So on top here we have the outside air, we have the glass, then the gas and the coating and another glass. So it would be good to have the coating, to bring the coating upwards so that it's underneath the top glass layer. And we can just reverse the stack here by a lot of mouse operations, using here clicks on these arrow buttons. But we can also use a shortcut. There is a command called manipulate, and that has a sub command called flip part of layer stack. So we can start here at layer number 2 and end at layer number 12 and reverse basically the whole layer stack. So now we start with 4mm glass, then the titanium dioxide, zinc oxide, first silver, and so on. So this is now the reversed layer stack, and now it makes sense to declare new fit parameters, basically the layer thicknesses, and let's do it only for the functional layers, for the layers that take an optical function, to have the more easy, a shorter list. So let's take the titanium dioxide, the first silver, the center oxide, second silver, and the top oxide, and put some limits here, 0 to 40 nanometers for the titanium dioxide, 0 to 20 for the silver. Center oxide, let's say maybe from 50 to 120, just to have some variation that we can play with. And for the top oxide, let's say a range from 20 to 80 nanometers. Okay, so here's the double silver solar control coating. I have to move it downwards. And so let's save this first using a new name. Double silver low E, or double silver. Let's call it double silver design. That's okay. So obviously now, since I added a lot of layers, the color is not correct anymore. The light transmittance is not as good as it could be eventually. We have the same wishes still. Let's press start again and watch if code can repair the colors and also increase the transmittance a little bit. Okay, that doesn't look too bad. The colors seem to be easy. They have achieved their target values almost. The U value is also very close to our wish of 1.1. And you can see here now, due to the additional layers, we have several wiggles here in the visible and the reflectance spectrum. So that gives some freedom of the model. And we will make use of that freedom for more advanced design wishes that we will have concerning, for example, angular color. And that will be treated in one of the next tutorials. For today, I would like to say thank you for your patience. I will save this configuration finally and publish it sooner or later on my website so that you can load it and use it as a basis for your own code work. Okay, thanks a lot for today.